Welcome back to the Deep Dive. Today we're jumping into a fascinating paper, PHYBench, Holistic Evaluation of Physical Perception and Reasoning in Large Language Models.
That's right.
So for the quick version, this paper introduces PHYBench. It's a new, really high-quality benchmark designed to test how well LLMs understand physics.
And we're talking a wide range mechanics, EM, thermo, optics, even modern and advanced physics. Difficulty levels span from high school right up to physics Olympiad stuff.
And they propose a new way to score these things, right?
Yeah.
The expression edit distance, or EED score, is not just right or wrong.
Exactly. It's based on the edit distance between mathematical expressions, giving a much more nuanced view.
The big takeaway, even the best LLMs out there lag significantly behind human experts. Like really significantly.
Yeah, the gap is quite striking. PHYBench really highlights that.
Okay, so let's dive deeper. Why this focus specifically on physics? Don't we have tons of reasoning benchmarks already?
That's a really good question, and it gets to the heart of it. Existing benchmarks, even the tough science and math ones, often miss the mark on physical reasoning.
How so? What's the difference?
Well, it's about grounding in physical reality. Abstract math problems are one thing, but reasoning about, acceleration, forces, energy, how they interact in actual scenarios, that's different.
Okay, so it's less about pure logic and more about understanding the rules of the physical world.
Precisely. And this isn't just academic. For general AI, for AI operating in the real world, think robotics, engineering this kind of physical intuition is absolutely crucial. PHYBench aims squarely at testing that.
Got it. So tell us more about PHYBench itself. What's inside this benchmark? 500 problems you mentioned.
Yep, 500. And they're carefully curated. As I said, it spans 6 major domains: mechanics, electromagnetism, thermodynamics, optics, modern physics, and advanced physics.
That's comprehensive. And the difficulty varies.
It does. High school, undergraduate, and then those really challenging physics Olympiad problems. The key thing is they're based on real-world physical situations.
And the answers aren't just numbers.
No, that's critical. The models have to derive symbolic expressions. Think algebraic formulas, the kind of thing a physicist would write down.
Okay, that definitely raises the difficulty level. It forces them to show their work, essentially.
In a way, yes. It tests if they actually understand the underlying relationships between physical quantities. They can't just guess a number or, plug things into a remembered formula without understanding.
And you don't need outside knowledge.
Correct. Everything required is in the problem statement. It focuses purely on reasoning from the scenario given. Plus, many problems require long chain reasoning, multi-step deductions. The model often has to sift through information, discard irrelevant details, and follow a logical path over several steps to get to that final symbolic answer.
Wow. Okay, this sounds incredibly thorough. How on earth did they put this data set together? It sounds like a massive effort.
It absolutely was. Very human-centric. The paper mentions, I think it's figure 2, the pipeline involves 178 students and 109 human experts, mostly from Peking University's School of Physics.
That many people. So what were their roles?
Well, you had compilers drafting the initial problems, then reviewers check them meticulously for clarity, accuracy, and making sure they fit the strict criteria.
And those criteria were?
3 main things. Text-based formulation only, a single unambiguous symbolic answer required equivalent forms are okay, but no equations or numbers, and crucially, unambiguous phrasing, no room for interpretation.
So tons of human oversight. Did AI play any part in building the benchmark?
It played a supporting role, yeah. They used GPT-4o for final checks on grammar and formatting, and they did some initial model testing during refinement to make sure the problems actually worked with the required answer format.
And where did the problems come from? Were they worried about models already having seen them?
Good point. They used a mix of non-public sources and some public ones, but specifically ones that aren't easily found with a quick web search. That helps mitigate the data contamination issue. It was a very iterative process, back and forth between human checks and some model testing.
Okay, so we have the problems. Now, scoring them. You mentioned the EED score. How does that actually work? Why not just mark them right or wrong?
Right, that's the standard approach, binary scoring, but it's often too coarse. Imagine a model gets the physics principles right, but makes a small math error at the very end. Binary scoring says 0 points.
Which doesn't feel quite fair if most of the reasoning was sound.
Exactly. The EED score expression edit distance tackles this. It looks at the semantic similarity between the model's answer expression and the correct one.
How does it measure similarity?
It calculates the edit distance between their tree structures. Think of the math expressions represented as trees. The score measures how many steps adding, deleting, changing nodes it takes to transform the model's tree into the correct one. Figure 6 in the paper has a nice visual of this.
So it's analyzing the structure of the math, not just the final string.
Precisely. It gets at the underlying mathematical relationships. This allows it to capture partial understanding.
How is the score calculated from the distance?
They use a piecewise linear function. Basically, the smaller the relative edit distance compared to the size of the correct answer tree, the higher the score on a scale from 0 to 100. A perfect match is 100.
Okay. And I saw something about subtrees.
Ah, yes.
Yeah.
They refined the algorithm to handle subtree edits like insertions and deletions with a reduced cost for bigger subtrees.
Why do that?
The motivation comes from physics itself. Often, an answer has distinct physical components, maybe a kinetic energy term and a potential energy term. If a model nails the kinetic energy part, a whole subtree, but messes up the potential energy, this scoring gives more credit for getting that significant component right, compared to just making scattered small errors.
That makes sense. So overall, the EED score gives a better picture.
Definitely. The paper argues it captures correctness better, measures capabilities more granularly, and it's better at distinguishing between models, especially when scores are generally low, as you can see in Figure 8 and Appendix A2.
Sounds much more informative. Okay, the moment of truth. What happened when they tested actual LLMs on PHYBench with this EED score?
They threw a whole range of models at it. Gemini 2.5 Pro, O1, DeepSeek R1, GPT-4o, Claude 3.7 Sonnet, some smaller 32B models too.
And the results?
The headline result, shown clearly in Figure 3, is the gap. The best LLM, Gemini 2.5 Pro, scored about 36.9% accuracy and a 49.5 EED score.
Okay. And the human baseline?
Human baseline physics undergrads from Peking University was 61.9% accuracy and a 70.4 EE score.
Wow. That is a big difference.
It really is. It shows just how challenging PHYBench is and how far current AI still has to go in this specific type of reasoning.
Did the type of model matter? Did the reasoning-focused models do better?
Generally, yes. Models like O1, designed more for reasoning, tended to outperform the more general LLMs, which isn't too surprising.
But any surprises?
Well, some recent general models like DeepSeek v3 and the latest GPT and Claude models were actually quite competitive, which is interesting.
What about the smaller models? The 32B ones?
They struggled. Really low scores across the board. The researchers think this might be down to the long chain reasoning needed for PHYBench and perhaps difficulties with the physical perception aspect that maybe aren't stressed as much in other benchmarks.
Right. And you mentioned the EED score itself was useful beyond just the score value.
Yes. Sample efficiency. Appendix B and Table 3 show that using the EED score gives, on average, something like a 300% boost in sample efficiency compared to just using accuracy.
Meaning you can differentiate models more reliably with fewer test problems.
Exactly. The nuance of the EED score makes the comparison statistically stronger.
Did they break down performance by physics topic? Like, were models better at mechanics than optics, for example?
They did. Table 2 and Figure 4a show performance across the 6 domains. And yeah, there were definite patterns.
Such as?
Well, for instance, some traditional models like GPT-4o seemed relatively weaker in mechanics compared to some reasoning-focused ones like O1, maybe suggesting issues with spatial or dynamic reasoning.
Interesting.
Thermodynamics also showed a pretty clear gap between the reasoning models and the general ones, perhaps because those problems often need complex multi-step thinking. Modern and advanced physics showed variations too.
And Figure 4a has that radar plot.
Right, the relative advantage plot. It's a neat way to see where each model shines or struggles compared to the average across all models for that specific topic.
What about problem difficulty? Did one model stand out on the really hard questions?
Yes, that was another key finding shown in Figure 4b. Gemini 2.5 Pro showed a noticeable advantage on the harder problems, the ones where all models tended to score lower.
So it has more robust reasoning power when things get tough.
It suggests that, yeah, on the easier problems, the performance gap between Gemini and other top models like O3 Mini or DeepSeek R1 was much smaller. So the current top models might be converging on easier tasks, but the really hard stuff still differentiates them.
Now, the paper talks about analyzing errors in terms of physical perception versus robust reasoning. Can you unpack those?
Yeah, this is super important for understanding why models fail. PP, physical perception, is about correctly understanding the initial setup.
like identifying the object's forces, the basic physics principles at play.
Exactly. Making the right qualitative judgments. The paper uses an example, problem 1 in figure 5, with balls and strings. A PP error there was misunderstanding the kinematics, getting the angular velocity wrong from the start.
So, fundamentally misinterpreting the physical situation. And RR,
robust reasoning, is about what happens next. The symbolic math, solving equations, applying the conditions correctly and consistently.
The mathematical heavy lifting.
Right. Example problem 2, the relativistic mirror one, shows an R error. The model set it up correctly using conservation laws, but then botched the algebraic derivation to get the final symbolic answer.
Okay, so PP errors are about misunderstanding the physics. RR errors are about messing up the math or logic steps.
That's a good way to put it. And crucially, the EED score is sensitive enough to capture both types of errors, reflecting issues whether they happen early in perception or later in reasoning.
This seems like a really valuable framework.
Yeah.
So stepping back, what are the big picture implications here? What does PHYBench mean for AI development?
Well, it provides a much more realistic and frankly humbling benchmark for AI's physical reasoning skills. It clearly signals that we're not there yet, not even close to human expert level for these kinds of tasks.
So it's a tool to guide future development.
Absolutely. It can help researchers pinpoint weaknesses and develop models that don't just mimic patterns, but can actually, build internal models of physical systems and reason about them reliably.
It's pushing for a deeper kind of understanding, beyond just pattern matching or knowledge retrieval.
Precisely. The paper really emphasizes moving towards AI that can autonomously construct these internal representations and derive physical insights through principled reasoning. That's the goal.
This has been a really insightful deep dive, so to quickly recap, PHYBench is a tough new physics benchmark, testing deep physical perception and reasoning.
Using symbolic answers and the nuanced EED score for evaluation.
And the results show a pretty stark gap between current state-of-the-art LLMs and human experts.
Highlighting challenges in both understanding the initial physics, PP, and carrying out the math correctly, RR.
It really makes you wonder, doesn't it? What's going to take? A new architectures, different training data, some fundamental conceptual shift to bridge that gap. And what happens when AI can reason about physics like an expert? The potential for science and engineering is just immense.
Huge potential.
For all of you listening, especially if you're in AI research, the PHYBench dataset and code are out there. It seems like a really valuable resource to explore and maybe test your own models against. Serious challenge for the field.
Definitely worth checking out.
Thanks for tuning in to this deep dive.